Here we go. I gotta remember the date. All right.
It's Wednesday.
I know. It's always Wednesday now. Hello, everyone, and welcome to the Weekly Space Hangout for Wednesday, September 27th, 2017. I'm Fraser Kane, publisher of Universe Today, and this week we've got our regular full cast of crew, our co-hosts here to talk about all the space news that's fit to talk about. All right. Right now on my screen, we've got Morgan Renberg. Morgan.
Yes.
Yeah.
First.
First. We've got
Don't be that guy.
We've got Kimberly Cartier. Kimberly.
Good evening, everyone.
Oh, come on, camera. Switch
So
to Kimberly.
professional.
Where is she?
Hello.
Oh, I feel like you're not projecting enough. The camera wasn't catching you compared to Morgan.
Good evening, everyone.
There you
I'm
are.
as cool as Morgan.
There you go. And last but not least, we've got Paul Sutter. Paul M. Sutter. I will get there, Paul.
You will. I'm just here.
We're going to be talking about we've all brought stories to discuss, but first we've got a very special guest, Jason Schneiderman from NASA. Jason, welcome to the Weekly Space Hangout.
Thank you. It's great to be here.
You are both a fan and a panelist, which I think is wonderful.
Yes, I am. So I've been listening for quite some time, and I met Pamela this spring, and that led to me to coming on here.
So, well, as always, I like to ask people who they are and what they do. So who are you and what do you do?
So I am a contractor with KBR Wiley at Johnson Space Center here in Houston, Texas. I wear two hats within NASA's Human Research Program. The first hat is I am the discipline scientist for what we call the behavioral medicine risk, which is the risk of adverse cognitive or behavioral conditions and behavioral and cognitive symptoms and psychiatric conditions. It's a mouthful. Basically, it's the brain and mental health risk. And the other hat, which is what I'll be mostly talking about, is I'm a scientist within our behavioral health and performance laboratory. And I do a lot of work in our spaceflight analogs as well as in human spaceflight itself. And by training, I'm a neuroscientist and a psychologist.
So you're the person who's going to help diagnose the space madness.
I'm the person who's trying to help prevent the space madness.
Or help them come to grips with the terrible, terrible things that they did in the grips of space madness.
Well, that's part of our plan, but we hope we never have to get there.
I've seen some Ren and Stimpy. I know how this turns out. So you're talking about, you've got what are some of the aspects that you're working with NASA to try and help them understand? What are some of the factors that play into this?
So the primary factor we're trying to understand its effects on the brain is isolation, confinement, and extreme danger. And then add on top of that the effects of microgravity, such as fluid shifts, and on top of that, the effects of radiation, especially once you get outside the Van Allen belts. So there's a lot of things to take into account. But as I said, we sort of break it down to primary and secondary risks. Our primary risk is sort of that isolation and confinement and separation. And the secondary things are the things like the microgravity and the radiation. There are other groups here at NASA that deal primarily with those issues.
But that idea of isolation and confinement and extreme danger, that has been, we've got opportunities here on Earth to test that out. People on submarines, people in Antarctica, sailors. Right?
So in some cases we do, but the thing is, for our at least near future plans, we're talking about very small crews. The Deep Space Gateway and the Deep Space Transit, we're looking at crews of 4 to 6. Our initial Mars missions will probably be somewhere in that range, possibly up to maybe 8 or 12. And whereas most people isolated, even the Antarctic or the Arctic, it's maybe 9 months a year. Round trip to Mars is 3 years. And it's an extreme environment. So we're talking about taking this work that's been done in environments like the Antarctic, like in submarines, and taking it to the next level of basically being extreme, decreasing the number of people, decreasing the size that they have to be in, what we call the habitable volume, and increasing the duration.
And you guys have done some tests already, right? Some tests have been done to sort of see how people do in these extreme confined areas for long periods of time in simulation.
Right. So we run what we call analogs, which some other people call simulations. They actually fall into two categories. One we call our ICS, which stands for isolated, confined, and controlled. And these are places like our facility HERA at Johnson Space Center. And there are other facilities throughout the world where basically it's a huge simulator. And then we have our ICE environments, or isolated, confined, and extreme. And those are when we go to places like McMurdo or South Pole Base in the Antarctic, where we currently have research deployed. And we've done experiments, either NASA or international partners or labs that we sponsor have done experiments over up to 1 year. And the longest one to date has been around 520 days. And that was done in Moscow a few years ago.
And so, I mean, it feels to me, and I'm sure, NASA wants to be absolutely certain, but it feels like psychologically, like the astronauts are the best of us. They are amazing. All the ones that I've met are amazingly well-balanced human beings. They get along with everybody. They should do pretty well in those kinds of environments, and we've seen human beings get together well. But there are, as you mentioned, there's not just the sort of these psychological issues of being in danger in a confined area, but there are actual physical dangers of being outside the Earth's protective magnetosphere.
And that's what we are worrying about, and part of the interaction that we're worrying about is what happens when you take somebody who, if they were on Earth and they were confined and they'd be fine, but then you expose them to space radiation or the fluid shifts of microgravity or the altered microbiological environment, because we have some evidence now that certain bacteria, for example, are more virulent in microgravity. And we're worried about the synergistic effects. We're also worried about, as I said, taking it to the extreme. On Earth, we really don't have people who are exposed. And yes, our astronauts, they are the best selected, best trained people in the world. But sometimes things happen that are beyond our control. And we want to be prepared for those. We want to be prepared for those extreme cases. And one of the major things we're trying to deal with is not only the personal psychology, but the interpersonal. And right now, our support for our astronauts is top notch. The International Space Station is a great place for them as far as their cognitive and mental health. They have real-time communication with the Earth, which also, not only is it the crew on the ISS, but there's a huge control crew here in Houston at Mission Control, plus in Huntsville at Payload Control, plus there's the one in Moscow. It's run by dozens of people. So basically, the crew has this huge support network in real time, and they have these beautiful views of the Earth. They can basically pick up a telephone at any point or Skype with their friends and family. They get fresh resupplies every few months, pending the occasional launch failure. They get care packages from home as part of those resupplies. The crew rotates out every few months. So there's a great psych support structure right now. But you take all of that away, take away the real-time communication, take away the resupply, take away the crew rotations, take away the view of the Earth, take away the large space that right now we have. The International Space Station is somewhere around a 4-bedroom house as far as habitable volume, whereas something like the Deep Space Gateway or Deep Space Transport, we're talking a fraction of that size.
Yeah, I mean, the Deep Space Gateway specifically is so small. It's this tiny, 4 modules right now. We're going to be talking about this later on in the show, but it is a very small place. And as you said, that is they don't have that same real-time communication. It's a bit delayed. It's going to be harder, days away from safety at that cislunar orbit.
Right.
They've got, each of those is one step more difficult. That sounds to me like the right strategy, though, to test out all of these, test these limits of human beings. And it's in that higher radiation area. So
I'm personally really excited about the Deep Space Gateway and the Deep Space Transit. Personally, first, it's nice to actually have missions on the books instead of just notional ones. And second of all, it really will give us the chance to do a lot of the shakedowns that we need, both science-wise and engineering-wise, before doing planetary exploration. Though our ultimate goal is to get out there to Mars. So if anybody's seen that, there's sort of exploration mission 11 is that Apollo 8 style Mars flyby. And unofficially, there's exploration mission 13, because every other mission is manned or crewed, I should say. And that one will be the eventual Mars surface landing. So
I didn't know the numbers had gone up that far. I think the last that I'd seen was like EM6 or 7, the one that was
currently the one that I've seen officially is EM11, which is the deep space transit, the Apollo 8 style free return around Mars back to the Earth.
Oh, that's fantastic. So do you think, I mean, you look at the work that's happening with SpaceX and, notwithstanding sort of the capability to send hundreds of thousands of people to go and live and die on Mars in this one-way trip, there is very little that has been discussed about sort of the psychological implications of going to Mars. And I always recommend to people, like, if you want to find out what it's like to live on Mars, if you're intrigued by that idea, go spend some time in Antarctica or the Arctic or the high mountains, because then it's inhospitable, but still, you could breathe. Do you
right? I mean, even in the worst environment here, which would be, say, the high Antarctic or high Arctic, you still have a few minutes before you die, as opposed to about a minute in space. But yeah, those are the best experiences, though short of our actual simulations. And by the way, we are actively recruiting people here at NASA to take part in these simulations. I do have to do this plug as part of my.
Oh, that's great! I'm sure you'll have some takers.
We are specifically looking for people who are astronaut-like, which means you have a background in science, engineering, mathematics, technology, or medicine, in your 30s, 40s, or early 50s, in otherwise good health. And basically, if you're interested, you can apply for our analog experiments. You go to nasa.gov/analogs, and there's information there about how to participate. And as I said, we're actively recruiting. Our major mission right now is HERA, which I could talk more about, which is our one here at Johnson Space Center, that I've been involved in since its inception about 5.5 years ago. So.
Yeah, absolutely. Why don't you give a quick explanation so people know what they're getting into if they sign up for HERA?
So HERA, I'm going to, for those people on the Hangout, I'm going to share my screen and show you a nice picture of it. It is a facility here at Johnson Space Center. It is a simulated habitat that originally was designed as a Mars surface habitat, and we're in the position of right now trying to reconfigure it to be more like the Deep Space Gateway. It's 2.5 levels. It is something that people live in for up to 45 days. And our current mission scenario is an asteroid retrieval mission. It is fully outfitted with as a simulator. So we have flight-like hardware in there. We use the same communication system they use on ISS. We use the same food that we have on the International Space Station. We use a lot of the same hardware and software, just in a much more confined space. The only thing we aren't able to simulate is the microgravity and the radiation exposure.
You could simulate the radiation.
Not ethically.
So, yeah, possibly.
And it's a 2-story. So the first story is what I'm showing on the screen now. I'm not sure if other people can see it, which is our, I'm gonna try to hide the other cameras here, which is basically what we call the lab and the workshop level. This is basically where people work. Our second level is where they eat and drink and exercise. And then the third level is sort of a loft. It's where they sleep. Again, if you go to nasa.gov/analogs, you can see pictures of this. What we do is we take 4 people who are astronaut-like and train them to take part in this 45-day simulated mission, which right now is an asteroid retrieval or asteroid rendezvous mission. This was started back still when the ARM was on the books. And as scientists, we like to do things repeatedly so that we get data from a large number of subjects, or in a lot of the cases, we're studying the team as a whole, the crew as a whole. So each mission is what we call an N of 1. So you imagine it takes several years for us to get up to do this. And so you arrive at Johnson Space Center a few days early, about 2.5 weeks. You're trained on everything from telecommunications to robotic arm operations, to how to fly the spacecraft, to how to do simulated EVAs, to how to do the science, all of the different, not just behavioral experiments, but the experiments about exercise, about food, about cardiovascular function, because HERA isn't just my laboratory's area, playground. It belongs to the entire human research program here at NASA. And basically what happens is after you're trained, you ingress into the module one night, and then when you wake up in the morning, it is as if you are docked to the International Space Station and about to leave. You undock and you're on your simulated mission on the way to a near-Earth asteroid, which is currently the one we're using is Geographos, just because we had lots of high-fidelity simulation information on it. During that time, we simulate things like the communication delay that you'd expect as you go further from Earth. We do things like we will purposefully induce things that are spaceflight like. For example, our major thing that we're working on this year is sleep deprivation.
Right.
Because one of the things we want to show, one of the things we're working on is measures to counteract fatigue and sleepiness among our crew. And recently, the International Space Station got these really great new lights that are LED based and are programmable. And we have actually installed these in HERA also, and we're using them actually to test out to see how good they are against fatigue and against tiredness and sleep loss. But other things can happen. We can simulate emergencies, all sorts of variety of system failures. We have a simulated life support system in there. And we can introduce, other factors such as manipulating workload, for example, the amount of work you're expected to do in a day. And we study all these different, just not how the person themselves adapt, how their bodies adapt, but also how they interact with each other within the crew and how they interact with mission control.
I mean, what's really interesting about these kinds of experiments, and you sort of got this feeling back in the Apollo era that I guess, as the flight hardware was improving, they were also able to sort of test the expanded capabilities and what it was doing to the crew, and they sort of went in lockstep. And now you've got this situation where we've been orbiting the Earth for a while, much to everyone's sadness, but now people are talking about these huge jumps to the next step, that we're going to be the Deep Space Gateway, and then they're going to go on the spacecraft to Mars, and then there's going to be hundreds of thousands of colonists living on Mars, and that the physical and psychological implications of this haven't caught up with the hardware that is being developed and being proposed.
Right. And in some ways, the International Space Station has been a great laboratory. It was built as a laboratory. And it's helped us to solve a lot of the issues, for example, around bone loss, around muscle loss, around cardiovascular deconditioning. But it doesn't really serve well for some of the, for example, neurological or behavioral changes that we see due to spaceflight. So that's where these analog facilities come in, is their ability to simulate what it's going to be like on the Deep Space Gateway and the Deep Space Transit, going beyond low Earth orbit again. And we're trying to get ahead of the technology curve so that we're not always playing catch up with the engineers.
I've got a couple of questions coming in from the viewers, and I just want to ask you one last question, which is that if you've heard the show, you've probably had me bring this up before, which is that I think with the plans, say SpaceX plans to colonize Mars and Mars One and folks like that, there's this expectation that human beings can live and thrive on Mars. But do we even know if a human being can exist in 40% gravity, 15% gravity of the moon for any long duration and be okay, and or even have multiple generations? I mean, do we even know if these things are possible yet?
No, and this is where it's exciting to be a biologist and medical researcher. There have been some research that have been done in animal models on longer term exposure. We've had humans in orbit upwards of a year. So we're starting to understand it, but really there are some great unknown questions here. And I'm sure that, life will find a way, humanity will find a way. We're adaptive, we're resilient, we're trouble solvers, we love a challenge. There hasn't been a frontier yet that we haven't conquered. But it's really sort of, we're at just that very first step of trying to figure this out.
So this question comes from Raza Siddiqui. Is there any research on hypersleep, deep sleep going? How is, this is the other way, is to just avoid the whole problem of having the astronauts interact, is have them take a nap and then wake up when they've arrived at their destination. How is that going?
So there is some research that's been going on in animal models on basically torpor or hibernation, extended hibernation. It's used medically for short periods of time. For example, you can go in for surgery, they bring down your body temperature, sort of force you into a hibernative state for a few hours while you're having things like open heart surgery or while they're trying to deal with something like extreme trauma. So we're just waiting on those incremental steps. We're nowhere near that. So for at least for the next few decades, we're going to have to talk about having a crew that's awake and functioning. Also, we're not quite there yet on autonomous systems. So the crew is, I think, going to be a valuable part. Even if some of the systems are autonomous and automated, we're going to still need people there to help troubleshoot. Because with things like rovers, if they go down for an hour, you always, you can wait for them to power cycle, you can wait for the batteries to recharge. When if you've got humans aboard, if something like the life support system goes down for an hour, you're kind of screwed.
Yeah.
So right now, all the mission planning we're doing involves a crew that's awake. But we are keeping an eye on the basic research that's going on in the biomedical field about hibernation.
Absolutely fascinating. So you're going to stick around, but I want to let people know where they can join this mission. Where can people sign up for the HERA mission?
So as I said, if you go to nasa.gov/analogs, there is a link. It'll probably be in the lower right-hand corner that says, do you want to participate? And there will be a phone number and an email address. So you can either call or you can send an email with your CV or resume to that email address. I won't bother reading it out here. You could go there, nasa.gov/analogs. We're working on having a online screener, but right now it's going to be phone or email. As I said, we're looking for anybody who's got a basically STEM background, is otherwise healthy, in their 30s, 40s, or early 50s. And this includes STEM educators. So especially if you have an advanced degree, that is if you have some graduate school training in either science, mathematics, technology, or medicine, and even if you are a K through 12 educator. Because we still have some educator astronauts in the astronaut corps. We have 2 going up very shortly within the next 2 years. So
fantastic. Well, thanks, Jason, for answering a bunch of my burning questions. But you're going to stick around, and we will cover some of the other news, and some of these are going to be very closely related to you as well. So I know you'll have something to say about this. I'm going to start with Kimberly this week.
Yes.
What's happening in exoplanets?
So lots of things are happening with exoplanets, but one discovery particularly near and dear to my heart, because it's very closely related to my PhD, was that there was the discovery of a hot Jupiter exoplanet whose atmosphere contains traces of titanium oxide. And this may sound very technical and very detailed, and you say, why do you care about titanium oxide? Essentially, titanium oxide is the holy grail of exoplanet atmospheres. It's what we've been searching for since we first learned how to detect exoplanet atmospheres, is this particular molecule, titanium oxide, because it seems to be theoretically the key for hot Jupiters, including this one, for having a stratospheric inversion. sort of like we have here on Earth, where on Earth, at least, the ozone layer, it's trapping harmful radiation, UVs and X-rays, and then bouncing them back upwards, essentially to protect us on the ground. What that does is it heats up the upper atmosphere just a little bit hotter than it should be. And it's sort of a key feature of our atmosphere and every atmosphere that we see in our solar system. So when we first learned how to detect exoplanet atmospheres, we really wanted to find one of these inversions somewhere else. Because essentially we don't like the solar system or Earth or anything to be in any way unique. So we're like, this has to happen somewhere else. We can only detect hot Jupiter atmospheres. How can we get an inversion? Titanium oxide's the answer. And we've been looking for it for like 15 years, and we finally found it.
So I was really interested in how they made this discovery, because normally when you think about finding molecules or elements in an atmosphere, you imagine watching the sun's light or the star's light pass through the atmosphere, and you take a spectrum and you look for the chemical signature of that in the spectrum. But when I was reading through this, it sounded to me as if they didn't really do that, and instead they were looking at the size of the planet as it changed orientation, and from that they were able to somehow infer the presence of this titanium oxide?
Right. So actually the two concepts are actually very closely related. The technique you're describing is called transmission spectroscopy, actually. And it's essentially very, very, very low resolution spectrum, like you could take with a spectrograph, where you're looking at the change in a planet's apparent size, or how much of the star's light is actually passing through the atmosphere at different wavelengths. So let's say you're at, one particular wavelength, the planet looks one size. You go to a longer wavelength, and the planet looks smaller because more of that longer wavelength light can make it through. So the atmosphere is blocking less of that light. And if you sample at fine enough wavelengths, you can actually pick out the absorption feature of water, or in this case, titanium oxide.
But this is also pretty great because it's a ground-based observation, right?
Yeah, that was something that I was very surprised to see, because what I did and what a lot of scientists have been doing is using Hubble Space Telescope or Spitzer in space to do these exoatmosphere observations. But this observation of WASP 19b was using VLT, which is from the ground. So I was really excited to see that. To see these kinds of really fine and precise measurements from the ground and not just from space.
So you mentioned that, the whole sort of being of astronomy is to make things boring, to make it so that nothing happening in our solar system is special relative to the rest of the universe. But our solar system doesn't have any hot Jupiters. So why should we sort of expect or want to see temperature inversions in hot Jupiters when we don't have any here? So maybe it would have been normal for them not to be there. Why did we think that there should have been a temperature inversion caused by titanium oxide?
Well, we see titanium oxide actually in the atmospheres of brown dwarfs, which in large part are the same size, the same mass, and the same temperatures as these hot Jupiters. Titanium oxide exists, vanadium oxide exists in these brown dwarfs. So we know that the molecule should be there and it should act this way, and we should be able to detect it. And now we know we actually can. And it's the first step to being able to detect these temperature inversions in the future in more Earth-like conditions, perhaps with my favorite James Webb Space Telescope.
That'll be next year.
I know. Don't jinx it, though. Don't jinx it. Crossing my thank you. Crossing my fingers.
Paul Metzetter, let's talk about the new discovery of another gravitational wave, but it's a little more exciting this time.
Yet another gravitational wave. At some point, we're going to stop reporting on individual ones unless something really exciting happens. What's
You
really
make it sound so humdrum.
You think that, except Kimberly's been talking about exoplanets one by one for years, and we know about thousands of
You
them.
just say you want to make astronomy boring. Here it is.
8,000
Gravitational
planets.
wave, nothing special. Whatever.
Yeah. Wait till we get to
Almost.
8,000 gravitational wave discoveries.
77th exoplanet.
Right. What is cool about this detection, it was not primarily done with LIGO. It was done jointly between LIGO and Virgo. So LIGO is two detectors in the United States. Virgo is a similar facility, same exact setup, but over in Italy. And so now we have a gravitational wave confirmed passing through all three detectors, which means the game is on. With three detectors, we can do triangulation. We can get a much better sense of where these sources are located on the sky. We don't just have a vague guesswork. We can pin it down to a particular galaxy, a particular location. And so there's nothing really particularly special about the two black holes that merged. It's within the range of the previous detections, what LIGO and Virgo are sensitive to. It's a 2 or 3 dozen solar masses per black hole, releasing about 3 solar masses worth of energy in the form of gravitational waves. But now we saw it 3 times. That's
Third
it.
time's the charm.
We're not bored
Yes.
yet.
We're not bored yet? Okay, fair enough. Fair enough.
So have
Now-
all the gravitational wave detections been these merging black holes? And is that a surprising thing? Because other things ought to be creating gravitational waves also, right?
Right, absolutely. So other things can create gravitational waves. Colliding neutron stars can create gravitational waves. A neutron star in a black hole can create gravitational waves. A supernova detonation can create gravitational waves. Inflation in the first 1 to 10 to the minus 20th second of the existence of the universe can create gravitational waves. But just as an analogy to astronomy, you have a particular telescope that's sensitive to a particular set of frequencies of light. And if some event happens at another frequency, you're simply not going to see it with that telescope. These gravitational wave detectors are tuned to a particular frequency range of gravitational waves. They can only see certain kinds of events. And there was an announcement, I think about a month ago, that LIGO may have seen the merger of 2 neutron stars. I don't recall if that was confirmed or not, or if that was just the hint of the detection. They needed to chew on the analysis a little bit more. But mostly with LIGO and now LIGO Virgo, you're going to be seeing colliding objects. That appears to be the sweet spot in terms of frequency and in terms of sensitivity for these instruments.
But the problem with this right now is that you can't, there's no other way to see these events happening. You've got this invisible collision between a black hole and another black hole. There's no other...
There's no optical...
or any other wavelength, right?
Counterpart, exactly. The exception is with the neutron stars, and so especially the possible detection announced a month ago, there was an electromagnetic counterpart, because when 2 neutron stars collide, they go bang, and we saw the flash, and so we're pretty sure we know the event that LIGO saw. We can see it with other means. But yeah, you're right, with black holes, we really had zero clue about the collision and merger rate of black holes until LIGO and now Virgo fired up.
And they turned this thing on, and 2 weeks later, they saw a pair of merging black holes. Is this telling us that space is a really scary place suddenly, and there's colliding black holes all around us?
Yeah, basically, the merger rate of black holes is higher than anyone really thought reasonable or justified. But that's the...
And are these all just in our galaxy, or are we seeing mergers in nearby galaxies like Andromeda too?
These are all extragalactic and very far extragalactic. We're talking these collisions occurred billions of years ago, and so they took place billions of light years away. These are all very, very far extragalactic events.
So if one happened in the Milky Way, they would be really obvious to these detectors, right? That would overwhelm.
Actually, maybe.
Does the distance change them?
No. It would be really obvious, because the frequency wouldn't change, but the amplitude would be very, very strong.
The problem with these detections, if I understand, is that it's the size. It's only a specific type of these black holes right now. It's these ones that are in this kind of mid-weight range because the stellar mass, they don't produce enough of a spike. They come together too quickly. The supermassive black holes, even though there is a lot of gravitational waves going on, it unfolds too slowly for the detectors to be able to pick them up. It's this perfect middle size where they come together in the right amount of time for those gravitational waves to be
like a
detectable.
stellar mass black hole, a few times more massive than the sun. That's like a dog whistle. It's too high frequency. It's too short for us to pick up. And then the supermassive black holes merging together or accreting material. That's like a subsonic vibration that if you pay attention long enough and beat your sensitivity down, you might be able to pick out that subtle vibration. But these medium scale black holes that we really didn't expect to be merging so much, these are like very loud pings that we can pick up really easily.
But and so now I guess, everything needs to have its holy grail. I'm assuming that with this now, the holy grail is you do get those, be it, neutron star detections or something where you can make some kind of other visual confirmation of this event happening at the same time. So you detect the gravitational wave and then you look on that part of space because now you've got that triangulation, you know where it happened. And so you look and you're like, hey, everybody, there ought to be something going on in Andromeda. And everyone goes and points their telescopes at Andromeda. And lo and behold, there's the event.
Exactly. And so it's building up that network, that infrastructure of doing rapid follow-up observations, of having robust databases of say, X-ray or gamma ray surveys or even optical surveys, so that when LIGO Virgo finds neutron stars colliding or a supernova detection, boom, we can go right to some other survey that also targeted the same patch of sky. And can give us the electromagnetic follow-up or even the neutrino follow-up if we're talking about some of these highly energetic events. So we can really paint a fully fleshed out holistic picture of what's going on. But when it comes to these black holes, like it's gravitational waves or nothing.
Morgan, let's talk about the horrible disaster that is Hurricane. Man, we're up to Maria.
Hurricane Maria.
What's happening with Puerto Rico and its effect on science?
Yeah, obviously, we all know that about a week ago, Hurricane Maria hit Puerto Rico as a Category 4 storm and has just wreaked, nearly unprecedented destruction across the entire island. And what's happening to all of the American citizens all over Puerto Rico is obviously by far the most important thing. It could be months before many of them have power and drinking water and access to communication. But there's important science assets on Puerto Rico as well, none more valuable to us than the Arecibo radio telescope. And fortunately, first off, the crew that operates the telescope all survived the storm just fine. And the telescope sustained less than catastrophic damage. You might remember Arecibo as a sort of 100-meter sized dish stuck in sort of like a natural depression in the ground pointing up. It's been the backdrop for a James Bond movie, for Contact. You can probably, if you think of a radio telescope, this is probably what you're thinking of. And sort of hanging on top of it is this giant, many tons secondary dish that reads the reflection of radio waves that are collected by this giant disk. And for the most part, that sort of precariously hanging structure survived the hurricane force winds. But a few sort of ancillary pieces did fall off of it, and they did strike the main dish, and they punctured it in several places. Now, a radio telescope dish is not like, say, the Hubble mirror, where it's very finely detailed. It's actually just sort of made of metal mesh. So it's not like you can't just sort of patch over that. Unfortunately, a lot of their operations buildings flooded as well. And the continued lack of sort of infrastructure on Puerto Rico after the storm, and the complete unimportance of Arecibo relative to getting people food and water and medicine means it could be weeks or months before crews are able to sort of really even get in there to start looking at the damage. And it probably is going to cost several $1 million to fix it up. And that's a problem, because Arecibo was already slated by the National Science Foundation, which is the primary funder alongside NASA, to close Arecibo and try to sell it off to a university or another user. And it's kind of been going back and forth over the last few years about whether they'd be able to find the money to keep Arecibo operational. And now not only do they have to find all of that money, but they've got to get this big lump sum up front just to repair the thing so it can start working again. And it's quite possible that this will place Arecibo's future in sort of perilous waters, where they might just say, okay, we're already thinking about getting rid of it. We're not going to put a lot of money into a car you're about to sell. Let's just scrap it and move on.
Honest question, Morgan. Would we miss Arecibo, not emotionally, but scientific output over the coming decade?
We would. And there's sort of two categories of things that radio telescopes do. One category of things that they do is they listen. So you're listening for radio signals coming in from astronomical events around the galaxy and throughout the universe. And there's actually a bigger telescope in the world, a fast radio telescope that was recently built in China that will be able to listen on many, but not all of the same frequencies that Arecibo can. And we have other telescopes as well, like the Green Bank telescope in West Virginia, the very large array out in the Western United States that can listen in many of these same ways. What sets Arecibo apart on this large telescope scene is that it can also transmit. And so what Arecibo can do that the giant fast telescope in China can't do is it can send a giant blast of radar essentially out into space and listen for that signal to come back. And this is how we were able to do things like deduce the shape of the asteroid that OSIRIS-REx is going to study. We've even sent that radar as far out as Jupiter and watched and listened to it bounce off of Jupiter and come back to the Earth, and understood the interior structure of Jupiter, just like we can use ground penetrating radar here on Earth to understand and look for oil and minerals and things under the Earth's surface. We've been able to use Arecibo to study the interiors of other planets in the solar system. And that's a capability that doesn't exist on any other large radio telescope.
Right. I'll play devil's advocate. That does sound nice, but it seems like a somewhat marginal benefit for the immense cost of maintaining it and then now repairing plus maintaining it.
Well, and that's exactly the conclusion that NASA and the National Science Foundation came to when they were evaluating the nation's portfolio of astronomy assets. And they look at each telescope and they balance the successful science that's being done against the cost that it is and whether there are other instruments in the world capable of doing that same science. And they looked at Arecibo and they tallied up that science against those costs and its competitors and ranked it near the bottom of telescopes sort of worth funding for the United States. And so I think your advocacy is exactly what the decision makers in Washington have decided about Arecibo. But there are people in the scientific community who vigorously disagree with that. And I think this is going to weaken their hand, not to the scientific merit of it, but to the feasibility of restoring Arecibo at this point.
I mean, the way the cycle this normally goes over time is that, some mission reaches the end of life and you think it's going to be done, and then someone finds the money for it and is able to move along and work at a fraction of its previous budget, and they, these missions and these observatories tend to have a much longer life. But in this case, if they already had this mission or this telescope that was right at the end of its life, and now it's suffered this damage that, as you said, it's gonna have to be the fixing it plus the maintenance. I don't like those odds.
Yeah, I think we just have to think about life after Arecibo. If these sorts of things, at narrow as they may be, are necessary. For example, if we would not have sent OSIRIS-REx or Rosetta to visit these comets or these asteroids without knowing sort of vaguely what they looked like, what can we do with the remaining assets that we have to recreate those capabilities where they're necessary in a sort of more timely, more cost-effective way than basically keeping a jungle fortress open for that kind of thing.
Yeah. And it's just just another example of how badly Puerto Rico has been hit. I mean, I'm still reading stories about just how awful things are down there and how badly they need support and power and diesel and food, and it's gonna get worse and worse before it gets better for a while. So this is tough. Well, so my story is I'm going to be talking about the Deep Space Gateway, which I didn't know that Jason. I didn't even realize Jason was working on it. So then the big news today is that. So up until this point, of course, the Deep Space Gateway. This is this idea of this satellite, this space station that's going to be docked at the sort of this cislunar orbit. So it's not going to be going around the moon. It's going to be going near the moon. And it was going to consist of 4 modules, and they're all going to be launched. They're going to be sort of the purpose for the Space Launch System. So after the Space Launch System does its EL1, does its first test launch without people, it's going to then launch the Europa Clipper. And then the next 4 missions, we're going to launch modules up to build the Deep Space Gateway. It's going to send up the power module. It's going to have a habitation module. I forget. There's like a control module, and there's one other. Anyway, and this was sort of the understanding was this was going to be NASA's work. And so today, the Russian Space Agency, together with NASA, announced that they would be partaking in the construction of the Deep Space Gateway as well. And this was a bit of a surprise. And, Morgan may even remember, we talked about this not like a year ago, that Russia was already backing away not only from other collaborative projects with NASA, but also, they weren't sure they were going to keep maintaining the International Space Station. And then earlier this year, they finally confirmed that they would be supporting it to 2024, and now it looks like they're going to support it to 2028. So they'll be around to the end of the International Space Station. And so with the Deep Space Gateway, with Roscosmos, with Russia's plans, they're going to contribute, right now it sounds like 3 modules to the gateway. They're going to contribute the docking system, which is sort of what they tend to provide on space stations. And they may as well contribute launches from their new heavy launch vehicle, which is called the Ankara, which hasn't even been launched yet, but it's going to be in sort of that SLS class heavy lift vehicle. So it's quite a sort of surprise. I did not expect this to happen. I expected sort of relations to continue to sort of get further and further apart. But in this case, Russia has said that they're going to be contributing significantly to the Deep Space Gateway. So since we've got Jason here, Jason, did this come as a surprise to you as well?
This came as very much a big surprise to me as well. The plans I've heard so far for the Deep Space Gateway have been U.S. focused, with possibly some European involvement or Canadian involvement or Japanese involvement. Sort of our people are involved in the U.S. operational segment of the ISS. And, as you said, they're going to launch it piecemeal. Once the HAB module is up there, every other launch, the SLS will then bring a crew of what was supposed to be 4 to the Deep Space Gateway. I am a little bit both excited and relieved, because the addition of the Russians brings that important multinational factor to it, which we know, most of the time when we talk about future space missions, we assume they're going to be international, and that seems to be the way they're going to be going. We're never sure who the players are going to be, but also the fact that it might not be as small as we thought it might, and something that had our team a little bit worried was the cramped quarters and also the limited ability to do science aboard it, because whereas the International Space Station has several modules dedicated to being laboratories. We weren't going to be seeing that on the Deep Space Gateway. It was basically going to be a shakedown for the transit to Mars. But hopefully now we can get some more science done while we're in cislunar space. So yeah, actually the first time I learned about it was in the pre-show.
Yeah.
So Jason, can you help me understand the point of the Deep Space Gateway? I think it'll come as no shock to our listener, because so here's what I mean. I can imagine sort of two purposes for it. One purpose would be to do the kind of research that you were describing earlier in the show, to do low gravity science, things like that. That seems fully covered by our $150 billion ISS. The other point I could see is as this sort of futuristic docking point for going out into space. And that feels kind of like building a parking spot for my flying car, in the sense that it's so speculative to missions we haven't really defined the parameters of, that it's ultimately not going to be useful at that task. And so it feels to me like, why did we build the ISS to study long duration spaceflight if we now have to build another space station to do the same thing?
Well, from everything I know, and I said I'm a contractor. I'm not very high up in the agency. Is that the Deep Space Gateway is meant primarily to be a shakedown for the Mars Transit vehicle, and that the Mars Transit, or what they're calling the Deep Space Transport, would be built out of the Deep Space Gateway. And it's basically, from what I understand, the chance to prove those technologies that we need to do multi-year missions in a small vehicle, such as life support systems that are completely closed loops and regenerative, with a crew, without that crew being more than 3 days away from being able to be rescued and sent home if something went wrong.
So why can't we bolt another module to the ISS that is a mini version of this, or just cordon off 2 ISS modules and say, this is the new Mars mission thing?
Actually, we're working on trying to do that. We'll see if that actually gets done. At least my group is very excited and trying to push towards doing some experiments on ISS. But one thing, as I said, there are a couple things that you really don't have on the International Space Station. One is the radiation environment. And it's not just the human, but it's the electronics and the mechanicals that can be affected by this deep space radiation environment. It's also going to be, as I said, somewhat of the communication delay. The moon, it's nowhere near as bad or cislunar as going to Mars, but it's enough that our standard telecommunications protocols that we use for the International Space Station will no longer work. So it'll give a chance to be autonomous.
But you simulate that already here on Earth, right? We could just wait a second before we answer every question from the ISS.
Unfortunately, the ISS is not built that way. The ISS is flown from Houston and from Moscow. So there is, you can delay some communications, but most operations you can't. And actually, we did work with a professor, Dr. Larry Palinkis, to do a small comm delay study on the International Space Station. But we were only able to delay that voice communication. None of the computers, none of the telemetry were able to be delayed, because the ISS is not flown by the astronauts. It's flown by mission control. Right. The astronauts are there to do the science and to do the engineering work.
I mean, part of this is just this idea of a capabilities-driven mission profile, which is like you don't know what it's going to take to live at that next level in space, and the only way to do it is to put a station there and have people spend some time there and shake out all of the questions. I mean, I think from my perspective, I would have preferred to have seen every step in between, higher and higher orbits, longer and longer durations, more and more people, before you make this jump from low Earth orbit to this cislunar orbit. But now that's the next step, and it makes sense as the next step before you go all the way to Mars or you try to land people back on the moon.
And so that's the way I think of it. It's, this is sort of like our early Apollo missions. the cislunar space. It's the shakedown of the vehicles, the shakedown of the technology before we go too far out where things, if they go wrong, that we can't, bring back our crew safely or repair it. And sorry, Kim.
Oh, no, it's fine. I was just going to say, I'm personally very relieved that we're doing this sort of intermediate step of putting the modules around the moon, where, like you said, there's still, 3 days, only 3 days to go if there's, heaven forbid, something goes wrong. I'm glad sort of we're testing out the technology and everything like that before we try and send people to Mars, where that, despite what Matt Damon would say, there's no rescue attempt.
On that note, I think we've reached the end of our hour. Sorry, Matt Damon, we're leaving you there on the surface of Mars. You are on your own. Thanks. Let's do a big thanks to all of the people who joined us. But before we do, I'd like to say, as always, a big thank you to the WSH crew. This is, of course, the community that keeps the chat going down there. They organize the guests, and they really are the partner in the creation of this show. So if you want to find out more, go to wshcrew.space, and you can join this community and participate in the live show. All right, I'm going to give Kimberly. Where do people find out more? What you're doing?
So as always, people can find out more by following me on Twitter at AstroKimCartier, or at my website and blog, which I admit I've not had time to update in a while, but that's KimberlyCartier.org. And of course, you can read all of my professional writing on Earth and Space Science at eos.org.
That's the problem. You spend so much time writing
I know.
that you don't have time to update your blog.
All the Earth and Space Science for other people, and, not for myself.
Yeah, I know the feeling.
But I learned all about snails last week, so it was totally worth it.
Morgan, where do people find out more?
I want to use my time to hear one cool snail fact from Kimberly.
So I learned about giant African land snails, which are an invasive species all over the world, and these snails can grow up to 8 inches long and weigh over a pound.
Oh my God, morganmember.com.
And sometimes they eat the plaster and stucco off of houses.
That's one fact more than necessary.
That's two.
That was two facts.
Now I want to go to the Deep Space Gateway, please. right now.
To leave
the snails.
To run from the super snails. Paul Metzetter, where do people find out more?
Yeah, I don't know how to follow up on snail facts. My website is pmsutter.com. I do podcasts and I write. Just go to pmsutter.com.
Sorry.
I can't beat that.
Jason, where do people find out more?
So there are two major websites you can find more about our work, nasa.gov/analogs and nasa.gov/HRP, which stands for the Human Research Program. I myself don't have a major social media presence other than my LinkedIn profile that's publicly available. You can search for me on LinkedIn, Jason Schneiderman, currently employed at KBR Wiley and NASA. I occasionally post on there, but I'm usually too busy in the laboratory or at HERA. So,
and thank you so much. You did just an absolutely fantastic job of staying on top of all of the comments and questions that were going on in all of the different chats. You that was the finest piece of question answering I think I've ever seen. So congratulations. That was fabulous.
Well, it was a pleasure to be here. And if any of the team from the hosts and the Weekly Space Hangout are in Houston and want to talk more, just let me know.
Oh, I can't wait to be trapped in. Maybe we should do that as a special episode. We'll all get trapped in the analog for a week and see if we can really work together. All right. So, of course, I'm Fraser Cain, publisher of Universe Today. As I mentioned earlier in the show, the thing you want to check out is our Instagram feed. We've got astronaut Terry Virts has taken over and is posting his exclusive photos and videos of his time on board the International Space Station, and they are so cool. So check that out. I'm going to bring in everybody. There we go. All right. Well, until next time, we'll see you all next week, everybody. Bye-bye.
Bye.